Hello, everyone. Good morning or good afternoon, depending where you're watching us from. My name is Melissa. I'm the host tonight. And today we're going to be having a webinar on enhancing MPD operations by using dynamic modeling for improved safety and efficiency. Today's presenters, we have Dr. G. Kao. He holds a PhD degree in oil and gas engineering and has 10 years R&D experience in well modeling, predictive analysis, and optimization. And he currently focuses on drilling digitalization and automation and digital twins and AI. And we also have Joseph Nabavi. Joseph Nabavi holds a master's degree in industrial asset management, and he has 10 years experience in IT systems with a particular emphasis on digitalizing drilling and well operations. So I'm gonna give the word to G so we can start with the webinar.
Hello, everyone. Very welcome to the webinar. My name is G, and today our topic is enhancing MPD operations with our dynamic modeling to improve your safety and efficiency. So before going to that, allow me to have a quick introduction about our company, the history. So e-drilling dates back to the research inaugurated at the Rockland Research here in Stavanger in 1989. With the main R&D research and the developments on advanced drilling modeling, model-based reasoning, part of the AI. The e-drilling idea started from 2004, and the company was founded in 2008, when we first launched the wellhead for real-time engineering and well ballast for controlled pressure drilling. Then a suite of software for drilling, like Well Planner for better planning your drilling operation, Well Map to visualize and navigate your well in visible subsurface in real time. And also in recent years, we proposed scalable and easy deployment with cloud architecture without getting rid of legacy systems. So microservices went to market in 2021, and a new product called Well Guide is ready for use for real-time operational optimization, including drilling, tripping, and other operations. Besides, we were also funded by government together with multiple collaborators to have a research on well control technologies for CCS wells. This is part of our dedication to reduce carbon footprints. So next, with more than 2 decades of R&D, now e-drilling has a suite of drilling software for the whole life cycle of drilling process, from planning, preparing to executing or reviewing your drilling operations. Those softwares has been used and verified by the industry for almost 2 decades. Those different pieces of software aim to meet different challenges in various phases of drilling using our unique state-of-the-art technologies. Today, we will be focused on MPD software, which is well balanced. But of course, if you are interested in other applications or software, you are more than welcome to ask for a demo. So back to well balanced, the MPD software. In general, it is advanced software to improve any of your MPD control system to better keep constant bottom pressure during MPD during your operation. It is enabled by accurate dynamic, thermodynamic, and hydraulic modeling. It is reliable to accurately control your pressure and help you to optimize your planning and specific procedures. How it works? It is embedded with any of your third-party control system with input from the operations, and it continuously simulates the pressure profile, temperature profile in the well, act as the brain of your MPD control system. Besides, a 3D visualization module is also available while drilling to help you to navigate to where you should pay attention to, like the ECD at casing and the pressure at the bottom hole, etc. So next slide, we have the software which has 2 modulars. One is the MPD RealTime. We call it well balanced to help you control and to provide set points for your MPD control system based on the dynamic real-time simulation. The other module called well balanced offline is used to plan, to test, to analyze your MPD operations and procedures. This is offline software that you can play with your computer, not in real time. Complement the real-time well-balanced software. The dynamic model mentioned accounts for essential effects for MPD, like dynamic surge and swap, various pump rates, drilling strain rotation, dynamic temperature effects, cartridge transport, and also set point pressure at any depth, even though we usually use it at the bottom hole. The supported operations, including drilling, reaming, running strains, tripping in and out, cementing, fluid displacement, static periods, and other dynamic tests like formation integrity test, leak-off test, and pore pressure test. So the superiority of this software is mainly due to the accurate dynamic modeling we have been used for this software. This has been verified and recognized by the industry for the last 2 decades. Compared with the commonly used steady-state models, it automates continuously modeling profile of real-time data and previously calculated data set. This result in accurate temperature and pressure profiles together with the fluid and cartridge transport. It also includes the transition period effects when changing operational parameters. Therefore, the drilling pressure margins are precisely narrowed such that you can reduce the uncertainty associated with your operation and as well as the operational risks. So the software has been used in many wells since 2010, especially in the North Sea, like we listed over here, the wells. And the counted operation for those wells are drilling, tripping, displacement, and cementing, of course, together with other tests, experiment tests. So this software has been successfully used, verified, and recognized for MPD operations. In next slide, we listed a few operational examples to verify the simulation, especially for first on the left is the dynamic FIT test. So the pressure, as you can see, especially in the middle, the blue dots increase stepwisely, and the simulated results can very well match the results of real-time measurements. And on the right figure, we have the dynamic drawdown as shown on the green dots, and the simulation, which is the line perfectly matched the whole process, which means the simulation is as accurate as possible. In next slide, we have for drilling and connection operations. So this is a predefined pump wrap up and wrap down sequence. So we try to simulate the process with our advanced model. Of course, as you can see, the flow out and flow in, as in the green dots, ramp down for a period and then ramp up. So it's a predefined sequence, and the results from simulation can perfectly catch the trend and the change, the dynamics in real time. So that's more like pieces of verification of our simulation. And next, let's join Yusuf for to the real play of the software. So Yusuf.
Thanks, Ji. I'm going directly to demo the software. Let me share my screen. Okay. Can you see my screen, Melissa?
Yes.
Yeah, good. Thank you. Okay. As G mentioned it, the well balance our system, there are 2 parts. The one part is offline well balance, which is used for the planning and the planning phase or optimizing of the planned operational parameters. So this one is a standalone software which can be used by itself to do any type of MPD or other type of simulations. So to run a simulation on this software, so you need some input data. Let me go through that quickly. If I click on the tools, let me show you. If I click on the tools, there is a well configuration editor. So they are the static data, or you need this data to input into the software to create a digital twin of the wellbore you are planning or you are going to drill, or any other type of operation. So for this purpose, so you need some input data, formation tops, pressure profile, pour pressure, fracture pressure, and collapse pressure. Temperature profile, they are static pressure, and then you have geothermal gradient here. Trajectory unit, tubular, both BHA elements and different type of the drill pipes. Bit, either you input the nozzles or you can only input the TFA. That should be okay as well, one of them. Wellbore geometry, you have here different casings, liners, and the riser. If you have an open hole, so you add your open hole here as well. Fluid, on the fluid, so you add rheology. If you have PVT table, gelling, and those parameters. Let's see if I click here. So you can add the rheology from the field, and if you have some more readings, so you can add here. PVT table. So here we don't have in this case, in the demo case, but you can add that as well. And then you have the gelling data. So these are the parameters that you input into the software, and then after that you run your simulation. So these parameters either can be directly imported from a third-party source, if they are available there, or if you have some Excel file or notepad file or anything of files, so you can copy and paste from the files inside the software. When that's done, so I'm basically ready to do a simulation. Let me, if I go tools again, so I see this one, dynamic hydraulics and temperature. So if I click that one, this window will pops up. So in this window, so you have a drop, this simulation I have already created just for the demo purpose, and it's running. So that's the reason they are gray. I'm not able to move the boxes around. They are closed now. If I stop the simulation, then they are becoming active, and then I can move them around. So, and then this boxes will become active as well. In the different type of simulations, so you just drag and drop the boxes from the left side inside this box to create your simulation. If you are drilling, very simple. You need a string movement, you need a flow rate, you need rotational speed, and then you need a connection. For the tripping purpose, you need only, let's say that here, this is the last line is we are pulling out a hole to show you later on. We can go through the plus as well to show you the surge and the swab effect of how the MPD system is working when you are pulling out a full BHA or any other type of, if you have liner casing for that purpose. So here you just add a string movement, and then booster pump is used like a trip tank pump here. So trip tank pump to fill the well when you are pulling out of the hole. And then you need a stop and connection. So based on what you need on different type of operation, so you just drag and drop here in a line. So one line of each line is one simulation type. So it's very easy. Just drag and drop, and that's it. You have a list view as well. You can edit here as well, but that's more difficult. We believe that the drag and drop down list is much easier. So you just drag and a box and put it there. So this simulation is now running. Let me put it on max. If you would like to run the simulation real-time speed, then you choose one, and then you can increase the speed. The max is the maximum, depends of your computer capacity. It's running if your computer capacity is very high, then it's running really quickly. So if I click on that, let me check. Yes, I'm on the max. So this is the time-based plot, as you see here. Time-based plot is here. I will go through the depth-based plots, which is updating while the simulation is running. So let me go through that first. Here you have some depth-based plot. These plots are along the wellbore. This is the zero depth for the well, and that's the bottom of the hole. So these values are for the whole wellbore, not only in one point. So these values are changing all the time as the simulation is running. Here you have, for example, the fluid velocity along the wellbore is, as expected, much higher around the BHA due to bigger string on the BHA and smaller unloose size. And then the laminar or turbulent flow, do you have a laminar or turbulent flow? It's laminar along the wellbore, except around a small portion of the BHA, because there are some stabilizers and other big elements behind the bit. So it's creating a lot of, the flow is getting turbulent. Here you have the cuttings along the wellbore, and then as you see, the cuttings is moving upward. I was finished with the drilling part. Now we are circulating out the cuttings. So that's why the cuttings is moving upward, but there is no more cuttings is created at the bottom of it. So we are finished with the drilling part, now circulating the whole killing. Here is the CTR. This is the velocity of the cuttings compared to the fluid. So it's showing you if your fluid is good enough, the flow rate is good enough, or your rotational speed is good enough to remove the cutting upward the well. And here you have the temperature profile. Both the red one is the unloose, and then the blue one is inside the string. This is dynamic temperature profile, changing all the time while you are circulating. Here is you have the pressure along the wellbore. The black line is more or less very small at the surface, only some bars, maybe 10, 15 bars, because we are keeping some back pressure, and then it's increasing downward. Here is some pressure loss in the unloose and inside the drill string due to friction. As you see, around the BHAs, the friction loss is much higher due to a smaller size on the BHAs. And then it's a bit higher in the unloose around the bit, and that's decreasing. Pressure ECD profile along the wellbore, and then you have the pore pressure and fracture pressure here. Then you see we are moving the cuttings almost out. So after this part, so let me just go quickly here again. So this was drilling part that was finished. That was the circulation, the whole circulating the whole killing here is still running this. And after this, we are pumping a bit heavier mat, means that we are moving to the displacing to tripping mat. So we are going to next is to move at this stage of the simulation. Once we are moving here, as you see, so you can see on the 2D tunnel as well, while the next fluid is going down inside the string and up through the unloose here. So if I go to the effect of the different parameters in the simulation, as G highlighted in one of his slides, that the air drilling's MPD model taking into account all the effects that you can have during drilling and tripping operations. So as you see, the temperature is higher. We are pumping here, cooling down the well. And then here is we are cooling down slowly, almost getting stabilized here. At this area, we start drilling. And you see, we are creating a bit cuttings around the casing shoe and around the BHA. And we are starting the rotational speed at the same area as well. As you see, when we start the rotational speed here, the dynamic or the set point, our set point surface pressure is decreasing. That's related to rotational effect. If you are rotating with this RPM, then you don't need that surface pressure. The surface pressure will be a bit lower. That's the effect of rotation on the surface pressure calculation. And then again, as you see, the surface, if I move my mouse a bit to the left, the pink one and the blue one, both of them is continuously decreasing until this point, and then stabilizing. The area which is decreasing, that's related to the cuttings. We have to start drilling, cuttings filling the well, and then the density on the well is getting higher. Then there is less surface pressure required to keep the same set point. And then here at this point, the whole well is filled with cuttings, and then it's getting stabilized. Here, as you see, so it's the surface pressure is increasing again. This again when you are circulating out the kick. So you are removing the cuttings from the well. So you need to increase the surface pressure while you are cleaning the hole, because you are removing the cuttings from the well. And then, so circulating the whole clean here. At this area, we start pumping the heavier mud, or you can call it the tripping mud, or you can call it the pill, that you are pumping a pill in the open hole. So you see the standpipe pressure start decreasing when I increase the mud weight here, mud density here, and then the standpipe pressure is decreasing. And then later on, when the heavier mud enters the annulus, the surface pressure is decreasing as well. So, and then at this point, we are pulling out of hole. When pulling out of hole, so if I zoom a bit smaller area now, so you see now pulling out of hole. When we are pulling out of hole, so the system requires higher surface pressure to compensate for the swap pressure while you are pulling out of hole. And then when there is connection, then this goes back to the same value as before. So that is all about the simulation is still running. I think it's not much left on this. It's 97%, almost completed. So as we are getting far away from, let me just zoom a bit quickly, a bit more. As you see, the surface pressure changes much higher at the beginning, and then it's decreasing upward. That's related that your bit is at this area, your bit is far away from the bottom of the hole, which you keep your set point, and then it's creating less swap pressure on that point, and that's why the surface pressure changes smaller. Let me move quick to the real-time one because of the time. Here is the real-time one. The other one was the offline mode of well balance. This one is the real-time. This is the model which can be embedded to MPD system and then control the set points, taking into account all the dynamics of the well, including temperature. So here you can connect that in two ways to the data source. Either you use with SML or OPC UA. OPC UA is preferred because that's changing in real time. There are some lags on the SML data, and that's not very preferable. Here you choose a set point. As you see my mouse on the left down corner. So you can choose the set point here, and then either you keep your set point at the bottom of the hole, or you can choose a set point and then you define the depth. Those depth you can define anywhere on the well. If I increase my set point now, let's see if I increase to 155, and everything is changing. As you see here, if I zoom a bit small. So you see my ACD is changing, and then the surface pressure calculation and everything is changing here as well. And then when you reduce the pump rate, so as you see the surface pressure is increasing automatically all the time. So this is the same thing. The input data here is the same thing. So you have the formation, pressure profile. This is exactly what I show you on the offline mode, means that when you have created your digital twin well configuration, you can use it directly into real time. So you don't need to spend time on that and create a new well configuration. So on the depth-based plot, you have exactly the same type of data that you had on the planning phase on the offline module. And so you can analyze your parameters in real time as well. One thing is that you are planning with some drilling parameters. The other one is that maybe some of the parameters will be different during real time. So you still have all your calculation, all type of your calculation available during real time MPD modeling as well, at the same time that you are holding your set point. I think time is finished, Melissa. I will stop here, and then if there's any questions, we can answer to questions.
Yes, thank you, Joseph, for the great presentation. So now I will be reading the questions from the chat. So if you guys have any further questions, please write it on the Q&A. So first question, maybe you can take this one, G. Have you embedded your MPD system to any third-party program?
Yeah, quick answer to that is yes. So we have our software has been used in multiple third-party well control system. For example, as mentioned in the previous wells, MPD wells from North Sea, our software is embedded in the Halliburton MPD software called Ballast. The MPD system. So it connects with our software to make the control to control the pressure, bottom pressure precisely for the real-time operation. That's just one example, but it has been embedded with multiple other third-party control system.
Okay, thank you, G, for answering this question. Next question for Joseph. How does the software retrieve data or connect with MPD system on the rig?
Normally, its system is using OPC to connect to different source of data on the rig side. Because OPC, the good thing with that is that that's changing all the time, where that's in real time. So you can use with SIML as well, but as I explained earlier, so there is a bit lag on the data. So it may require that you are not able to keep the set point during real operation as you would like to do. Because when you are embedding the system, our MPD system to a third-party MPD physical system, then we are providing the expected surface pressure, and based on that, the MPD system will close and open the choke.
Okay, thank you, Joseph. And last question. How many approximate clients are using your product per day? I think you can take this, Joseph.
There's, as G mentioned it, so Halliburton, Geobalance and North Sea, they are using the online, both offline and online version of MPD in the last 10, 12 years in many wells. In addition to that, our MPD training facilities has been used by many companies, and is all using that today as well. To verify their procedures, to verify their MPD choke, to verify their how their MPD chokes working, to test their MPD chokes and so on. And then the offline version is used by, if I remember correctly, by 3-4 customers right now. They are using that all the time to plan their wells.
Yeah, just a few more comments to that is, as you've said, the software can be used for multiple purposes. For example, training engineers with the MPD operation. That's that's widely used together with other softwares like the visualization software and the other simulation software. And also for the MPD, we have both offline and online. Some collaborators have both of them, and some has well planner for the planning phase, which is well balanced offline. So together there are many users and collaborators, and also it depends on your purpose for how you want to use them.
Yes, so our time is finished for today. So thank you everyone that participated on our webinar and that has sent the questions. We really appreciate you guys joining us, and I hope you all have a good day. So goodbye